So, hello everyone. Welcome to EEEE Lecture number 42. Okay, let me add the writing pad wire. Wait a second. I guess my writing pad is giving some trouble. Just give me a second. Okay, I guess it's settled down now. So, let us start with lecture number 42. Today's date is 28. I hope the PDF is visible now. So we will be building an equivalent circuit of a practical transformer. Why we require equivalent circuit of a practical transformer is it will provide the complete details of the current and the components, voltages, winding parameters of primary as well as secondary winding of a transformer are all represented in a common electrical circuit. So it will provide the complete details for the current and your components, voltages, winding parameters of primary and secondary winding. Okay, so all in one common circuit. So that will be helpful in predetermining the behavior of the transformer. See, predetermining the behavior of the transformer under various load conditions of operation. Okay, so transformer also work with different kinds of loads, no load or inductive load or a capacitive load. So that will be easier for us to analyze if we know the equivalent circuit of the transformer. Alright, so let us start. So this is a practical transformer with a load. So here V1 is my primary voltage, E1 is my self-induced EMF, I1 is my primary current, this is my iron core. Okay, this phi is the main flux which is shared in common with primary and secondary winding. E2 is my mutually induced EMF, I2 is the secondary current, and V2 is the secondary voltage. Alright, so this is the diagram of a practical transformer with load. Last time I guess when we have stopped discussed about a practical transformer with no load. Okay, so a practical transformer equivalent circuit we will have to draw now. So before that we have to set certain things apart. So let us see, go to the previous PDF. You remember before we have shifted our attention to the impedances, we have reached over here. This was the circuit which we have discussed. Can you tell me what is R1 and R2? Winding resistance at the primary and secondary. R1 and R2 is the winding and the secondary winding resistance. X1 and X2 is the primary and the secondary reactance. Okay, so this much we know. Yes or no? So this is my practical circuit of my transformer. Now few other things are getting added. Practical equivalent circuit, as we have seen that if the transformer is on no load, there are two more currents flowing in the primary side. Okay, so that current is I naught, which is IW plus I mu. Do you agree on this or no? Last time we have discussed this, right? So we have two components. One is iron loss component IW, and one is magnetizing component I mu. So I naught will be I mu plus IW. Okay. So this was the phasor diagram. I mu was in phase, and this R naught I naught current will be is the equivalent of IW plus I mu. I guess we have done these things right. So W naught is V1 I naught cos phi naught, and Wi, that is iron loss, will be V1 I naught cos phi 0. So this is what we have discussed. IW supplies for the iron loss, and magnetizing component is in quadrature with V1. So I guess we have done one thing wrong, I guess. I'm not sure. This should be I mu and this should be IW. Last time we have made this, I think, mistake. So please correct it. This should be IW, this should be I mu. Please check it if we have done it this way. I think we have written opposite, right? Yes or no? Anyways, this is the phasor diagram at no load. So basically what I am saying is, in the primary side we have two more currents, IW and I mu. IW is the useful current, and I mu is the wattless current. Here you have written iron loss active or working component IW is in phase with V1. So yeah, it is in phase with V1. So yeah, I guess this will be I mu only, IW only. Last time we have done it correctly only. This is IW, which is in phase with V1, and this will be quadrature phase, which is 90-degree apart. So that was correct. No, don't make any changes. Okay, so I naught is the vector sum of IW plus I mu. So this is in the no load condition. Now today we are drawing a practical transformer equivalent circuit. Right? So let's draw it together. So here in the primary winding we have R1 due to the primary winding resistance. So this is R1. Then we have X1, we know because of the primary flux leakage. Then we have this transformer primary winding. Then we have the iron core. Then the secondary winding. And in the secondary winding we have winding resistance R2 and a small inductance representing the effect of leakage reactance. And this transformer is loaded. That means output is connected to a load. This is plus minus V2, and the impedance of this load will be let's say ZL. Alright, okay, and over here we can show primary voltage V1 and primary current I1. Alright, here we have secondary current I2. This voltage over here is E2. This voltage over here is E1. So because of E1 there is E2, because of E2 there is V2, if this is not connected open. Now one more thing is missing, which is the effect of no load. So this also have to be included. So we have two components, IW and I mu. So IW component will flow through this resistor and I mu will flow through this inductor. So this will represent that this is IW component and this is I mu component. This is I naught current which was present over here, right? I naught current was a vector sum of IW plus I mu. So this is coming from here. Are you understanding? This IW plus I mu is coming from here. Under no load condition, what will be the effect on the transformer on no load? So yeah, this will be coming. We have a iron loss component and magnetizing component. Are you following? Can you reply? So please draw this diagram. This will be R naught. This will be X naught. Did you follow this? Or let me explain again. Followed?
Yes, sir.
Okay. Now, since this I naught current is due to no load conditions, we have two components, IW and I mu, which are flowing through a resistor and a inductor, which is correspondingly R naught and X naught. So this current, primary current, changes to I2 dash. Now I2 dash will be I1 plus I naught. Okay, just a reflection of adding these components. So these components are extra, which have been added in the circuit. Okay, so because of that this current becomes I2 becomes I1 becomes I2 dash. Alright, so please complete this diagram. This is the equivalent circuit of a practical transformer. This is the first step towards drawing the phasor diagram of a transformer. um, Let me know when you complete it. So remember over here, I naught is a vector sum of IW plus I mu. I mu is the useful power and IW is the useful power. I mu is the What less power? So this is the equivalent resistance of a practical transformer. Okay. Here the winding resistance are represented as R1 and R2. No need to write this because we already know that. The leakage reactance is represented as X1 and X2. Have you completed drawing the diagram? Can I go to the next one? Next page?
Yes, sir.
Okay. Then the no load current, this I have already told you. The no load current is divided into two parts, IW and I mu. Okay. Current IW is in phase with voltage V1. That's why it passes to a resistor. Because current and a voltage doesn't have any phase difference when it passes to a resistor. So I mu lags behind the voltage V1 by 90 degree. Why? Because over here, if we see carefully, this is IW, this is I naught, this is inductor, and this is I mu. Okay, so IW is in phase with the voltage V1. That is fine. That is absolutely fine because it is in parallel with V1, right? Here you see. Okay, they are in phase. Then your I mu is lagging behind for by 90 degree behind voltage. So what lags behind the in which component current lags behind the voltage by 90 degree in a inductor. So that's why this is an inductor XO and this is RO. Okay, so in the equivalent circuit above, I naught is represented by a pure inductance X0, which is taking the magnetizing component I mu, and a resistance RO taking the working component IW. Okay, and RO and XO are connected in parallel. Here they are. They are connected in parallel with the primary circuit. Okay, here it is. So RO represents the core loss. Okay, so what is the core loss of a practical transformer? I square R, that is IW square into R naught. Alright, so I naught is IW plus I mu. This is what we know so far. Understood this much? Can I go to the next one now? Now,
Yes, sir.
an exact equivalent circuit of a transformer referred to the primary side. What do you mean by refer to the primary side? Don't connect anything at the secondary, connect everything at the primary side of the transformer. So if you want to draw that, can be obtained by transferring the entire secondary circuit to the primary side. Okay, so if this is my transformer with the primary and the secondary side components, now I want to transfer this R2 and X2 on the primary side. So what will happen? Do you remember what do we did? So if we transfer anything from the secondary to the primary, that component has to be divided by K square, right? Hello? Do you remember? K or K square when we transfer anything from the secondary to the primary? Let us see in the last PDF what we have done. So if we want to transfer anything from the secondary to the primary side, we divide that by K square. Here it is. See? Okay. So this is what we will do now also. If we want to transfer this R2 X2 to the primary side, so it will become R2 upon K square, X2 upon K square. Okay, so let's draw the circuit now. So primary circuit will remain the same. Okay, let me start drawing over here. You all can draw along with me. So we have R1, X1. This is my primary voltage plus minus V1. This is my primary current I1. Then we have that magnetizing component, and this is R0. This is X0. This is I0 current. Okay, this is IW. So this much is the primary component. Okay, now we have added those components over here. So this is this is from the secondary side. So from the secondary side we have R2 is called as R2 dash, which is R2 upon K square, and x2 is called as x2 dash, which is x2 upon k square. So here we show the current as E1, and if we want to show E2 dash without showing the transformer, we can show it over here itself. E2 dash E2 gets transferred by E2 by K. Okay, this gets extended, and here we have the load. So I have not even shown the primary or the secondary winding here directly. So ZL dash becomes ZL by K square, and V2 becomes V2 dash, which is V2 by K. Okay, yeah, are you following? So which all components got changed? R2 got changed to R2 dash, X2 got changed to X2 dash, E2 got changed to E2 dash, which is E2 by K. Then ZL dash it changed to ZL upon K square, and V2 dash it changed to V2 upon K. So please draw this diagram. So these are the changes I have highlighted in yellow color without even drawing anything. And the secondary current changes to, here it was I2 dash, which is given by I2 into K square. Remember, the current gets multiplied by K square. Only the current gets multiplied, rest all gets divided. So this is the exact equivalent circuit of the transformer referred to the primary side. Completed this diagram? So in this diagram, all the secondary winding resistance R2 and the reactance X2 are transferred to the primary by dividing them by K square, where K is the transformation ratio. Okay, E2 and V2 in secondary becomes E2 by K, V2 by K. Okay, here I have shown already. Secondary current is transferred to the primary by multiplying it by K square. Okay, understood. So now what do we do next is next we shift the parallel branch to the input side. Okay, we will do this so that the primary and the secondary impedances or resistances are referred to the primary can be added conveniently. Are you understanding what I'm saying? These are primary resistance and reactance that can be added with the secondary resistance and secondary reactance. So that's why we shift this I naught on the left hand side. Okay, so just the same diagram I am doing it again. Just remember this. Can I go to the next one now? Have you completed the diagram? Yes, no?
Yes, sir.
Okay, now I'm just doing the job of shifting this branch to the left hand side, to the left of R1 and X1. So that's what I will be doing it here, shifting the RO and parallel to XO branch to the input side. So that is what we will get. So let's draw it together. Okay, so we'll start with this R1, X1, R2 dash, X2 dash, then we have ZL dash, here at the output we have V2 dash. Alright, and here it comes, this is I naught, this is RO, this is XO. So that is what we have done. We have shifted this RO parallel to XO branch to the left hand side. This is plus minus V1, this is I1. Now we write the currents now. This current will be I2 dash. This X1 and X2 will be as it is. This voltage over here will be E1, and this voltage will be E2 dash, which is E2 by K. R2 dash is R2 by K square. X2 dash is X2 by K square. ZL is equal to ZL by K square, and V2 is V2 by K. I have written these only, na? Just check. Yeah, this only. Please draw this. So this current will be IW plus I mu. Alright? Okay, have you completed drawing? Yes, no, what? Hello? Completed it?
Yes, sir. Done.
So now I can combine these things now. R1 and R2 dash are in series. So I can combine this to one and call it as R1 plus R2 dash is RO1, which is nothing but R1 plus R2 upon K square. Okay. Similarly, X1 plus X2 dash is X01. This is R01, X01. This will be X1 plus X2 upon K square. Alright. So this gets simplified now. I have only one resistance and one impedance, that is R01 and X01. So let's draw the modified diagram due to this. What does the diagram become now? It becomes quite simple. So this gets converted into, there are two components over here, RO, XO, and here we'll have only one resistor, RO1 now, and here we'll have one inductor, XO1. Rest everything as it is. So this is ZL1, and this voltage will be V2 dash. Okay, this current will be I2 dash, this current is I1, this current is I0. So this is plus minus V1. Okay, so here we have current as IW, here we have current as I mu. Okay, please complete this diagram now. So this diagram gets simplified into this now, where RO1 is R1 plus R2 dash, XO1 is X1 plus X2 dash. So please draw this diagram now. This is called as approximate equivalent circuit of the transformer referred to the primary side. So this is approximate equivalent circuit of transformer as referred to the primary side. Okay. So we have three currents, I1, I0 and I2 dash. Then we have V1, then we have V2 dash, ZL dash, RO1 and XO1. This is the approximate equivalent circuit of a practical transformer. Completed? Yes or no?
Yes, sir.
Okay. Now tell me what is RO1 plus XO1 can be called as? What is this called as? So this together is called as ZO1, which is nothing but ZO1 square will be RO1 square plus XO1 square. Yes or no? So where RO1 is R1 plus R2 dash, which is R1 plus R2 dash, R2 divided by K square. X1 is X1 plus X2 dash, which is X1 plus X2 dash by K square. And Z01 is, we can write it as RO1 plus J X01, or it can be written as Z1, Z01 square, which is RO1 square plus XO1 square. Okay, or it can be written in rectangular form, RO1 plus J XO1. So this is the equivalent circuit of a practical transformer referred to the primary, this diagram. Okay, so the main this is figure number 4. So the main parameters of the circuit are RO1, which is the equivalent resistance of the transformer referred to as primary side. XO1 is the equivalent reactance of the transformer as referred to the primary side. RO is the equivalent core loss resistance, and XO is the magnetizing reactance. So these are all what they are called as the main component parameters of the equivalent circuit. Please note them down. RO1, XO1, RO and XO, what they are called as. And this is my equivalent circuit as referred to the primary, this one. Okay, have you completed up till here? Can I go with the transformer on load circuit diagram and hence the equivalent circuit now? I'm phasor diagrams. Okay, now please concentrate on transformer on load. Okay, that is the next topic. We have studied transformer on no load and we have drawn its practical circuit, and now we are drawing we have to draw the phasor diagram for transformer with load and without load. So when transformer is on no load, the secondary current is 0. So here you can see from here, when the secondary winding is open, that means I2 is 0. The primary winding draws very small current in the form of I0. And I0 is what? Given by? Can you tell me I0 given by? We have repeated this many times today. Yeah. What it is called as? I0 divided into how many currents? Hello. You are there? Let me know. I0 gets converted into two components, no?
I1 and I2.
No, IW plus I mu. Correct? Okay, fine. This this writing pad is giving some trouble. Okay, yeah. Let me change my wire over here of the writing pad and let's see if it works. Is it okay? I think it's working now, right? So I0 gets converted into two components, IW plus I mu. You should remember that. So in no load condition, I2 is 0, and so I1 will be I0 plus I2 dash. Okay, so no, not this I2 dash. I2 dash is not there, so I1 will be equal to I0. Alright, so primary current draws a very small current I0, and phi is the main flux of the core. When the secondary winding is loaded with a load, let's say we connect an inductive or a capacitive load or a resistive load, the secondary current I2 is set up. The magnitude and the phase of the secondary current with respect to V2 will be determined by the nature of the load, of course, right? If it is resistive, then I2 and V2 are in phase. If it is inductive, I2 is lagging behind the voltage by 90 degree, or if it is capacitive, I2 will lead the voltage by 90 degree. Okay. So when the transformer is connected to the load, the primary have two currents, as I've already told you. One is I0 and one other is I2 dash. We have written it, right? So I0, I1 is I0 plus I2 dash. Okay, so total primary current will be the phasor sum of I0 plus I2 dash. This you will remember. Please write it down. And I0 is itself depend upon IW plus I mu. I mu equal to, this is equal to, let me rewrite it. I0 itself is equal to IW plus I mu bar. Okay, so now we are coming to the important parameter of topic of phasor diagram. So first we'll draw the phasor diagram with load and without load. All of you ready? So put this inside the
Yes, sir.
box. I0 is IW plus I mu. I1 is primary current is I0 plus I mu. I0 plus I2 dash. So first topic, write down phasor diagram of the transformer without considering winding resistance and leakage reactance. Means that R1 X1, R2 X2 is not there. Okay. So meaning R1 X1, R2 X0 not there in the circuit. Okay. So draw the circuit diagram now. It will be without them. It will be I1, I0, R0, X0 will come. V1 and E1 will be there. Then we have a mutually induced EMF E2. Then we have a secondary voltage V2, and here we have a secondary current I2. Here we have a current I2 dash, which is given by I1 plus I0. Okay. So please draw the diagram. They rarely ask this phasor diagram, but we are discussing it. Sometimes they ask the phasor diagram without considering winding resistance and leakage reactance also. Remember here I1 is I0 plus I2 dash. Okay, completed. Please draw it. I'll give you some time. On the primary side, note that E1 and V1 are equal but of opposite phase. So basically E1 is equal to minus of V1. On the secondary side, V2 and E2 have the same phase. So E2 is equal to V2 in the secondary side. Now we have to draw the phasor diagram for the following loads, for a resistive load, inductive load and capacitive load. So are you ready? Draw the phasor diagram for this circuit, this practical transformer. Yes, can we start?
Yes, sir.
Okay, and remember this diagram. I1 is I0 plus I2 dash. Alright, E2 and V2 are same. V1 is equal to minus of E1, that we should remember, and I0 is IW plus I mu. Let's start with the resistive load. So write down phasor diagram when the load is resistive, and this is for without winding resistance and leakage reactance. So without R1, R2, X1, X2. Okay. Now since we have a resistive load, as I've already told you, since we have a resistive load, I2 and V2 will be in phase with each other because the resistive load. Because we are drawing the phasor diagram for a transformer on load, practical transformer on load. And E2 is equal to E1 because K is 1. K is the transformation ratio, will be E2 upon E1 with K, which is 1. So E2 will be equal to E1. Agree? Phi is my reference phasor, so all the diagrams are drawn with respect to phi. E1 is equal to minus V1, that we already know. And I1 is I2 dash plus I0, I0. This we have to remember. Okay, so let us start. First, draw the reference phasor. This is phi reference phasor. So we start with a reference phasor. Okay, tell me where will V1 come? Even. Let me start with something. Let's say you can tell. Actually, I will be difficult to read the comment. You can orally tell. Let's say we have this V1 over here, V1 bar. Okay, where will I draw E1? Can you tell me? It's minus of.
Negative y-axis.
Yes, correct. Here it is. So here it will be minus E1. Yes or no? Okay.
Yes, sir.
Acha, tell me. Now next will be where will V2 and E2 come? What's the relation between E2 and E1? See,
E2 is equal to E2.
yeah, E2 is equal to V2, but how is E2 related to E1? Transformation ratio, na? Transformation ratio is 1, so E1 is equal to E2, correct? So same diagram is equal to E2. Yes or no?
Yes, sir.
Actually, it's negative, so no need to write. Already it's negative, so no need to write negative sign, and that is equal to V2 bar. Agree? So E1 will be equal to E2 will be equal to V2. Let me write it properly. So first of all, this was E1, which became equal to E2 because transformer ratio is K1, and that is equal to E2 V2 bar. Now, tell me the difference between the I2 current and V2. What should be the phasor diagram? Resistive लोड है ना, तो कितना फेज डिफरेंस होना चाहिए? जीरो ना?
0.
So it can I draw it like this in the same phase? This is I2. Is this correct? Yes, because
Yes.
here the phi 2 phase difference is zero. Phi 2 is the phase angle between V2 and I2 dash. So it is sorry, V2 and I2 I2 bar. So that is correct. Now where will I draw I2 dash? See, I2 and I2 dash के बीच में relation क्या है? Minus. They are both opposite sign. So where will I draw I2 dash?
Positive y-axis.
Yes. So this is I2 dash. But what is I1? Vector sum of I0 plus I2 dash. So where will I0 come?
In the first quadrant.
Yeah, it will come in the first quadrant, but where? Remember we have drawn the phasor diagram last time. Let me show it to you. ये बनाया था ना हमने I0. Yes or no? This
Yes.
phasor diagram we have drawn. So I0 has a slightly, if this is V1, okay, I0 will come in the first quadrant. Yeah, true it is. But I'm not showing IW and IMU here. So where it will come somewhere around over, let me draw it. Some angle will be there, but it will be drawn, let's say, uh, over here, maybe I0. Okay. Now how to draw I1?
Between I2
Parallel.
dash and I0.
Parallelogram, na?
Yes.
Here it is. Okay. So this is I1 dash. Alright. This is I1 dash. Agree?
Yes.
Acha, where will I draw phi 1? Angle phi 1 will be between I1 and V1, right? So here it is. Correct? If I draw it like this over here, I1, phi 1. Phase angle between V1 and I1 is phi 1. Phase angle between V2 and I2 is phi 2. Here phi 2 is 0, phi 1 is here present. So this is the phasor diagram when the load is resistive. Complete the diagram, please. Understood how to draw it?
Yes, sir.
Please draw it. Quickly draw it because we have to complete the other part also. Now can we go to load inductive? Lagging power factor, K is E2 equal to E1. Yes? Everyone?
Yes, sir.
Okay. Yeah, remember, in a low inductive load is connected at the output, right? So if this is the transformer, okay, so this is I2, this is plus minus E2, here is my load. So load is connected at the output. So if the load is inductive, can I say current lags behind the voltage by 90 degree? Yes or no? So I2 is lagging in an inductor. In an inductor, I2 lags behind the voltage, current lags behind the voltage by 90 degree. Agree on this? And I1 is I0 plus I2 dash. Okay? E2 is equal to E1. What we can say, V1 is minus of E1 and E2 is same as V2. These all things we know. So we'll start with the reference phasor over here, phi. First we'll mark V1. So if let's say this is V1 bar, will be V2, sorry, E1 below. So this will be E1 bar, which is equal to E2, which is equal to V2. Correct? Now, um, tell me where will this will come? I2,
X-axis.
which x-axis?
Positive X-axis.
Where exactly?
The reference line like the phi angle.
Yeah, I am saying it's an inductive load where V2 is lagging behind a voltage with an angle of phi which is less than 90 degree. It's not a pure inductor. So less than 90 degree matlab where it will come now? Here, right? Less than, na? Yes or no?
Yes, sir.
So it's lagging behind. So this is phi 2. So phi 2 is the angle between V2 and I2. So phi 2 is the angle between V2 and I2. That's and phi 1 is the angle between V1 dash and I1. So next value can you tell me, can I say this I2, if I extend it over here, this becomes I2 dash? Yes or no? Correct, na?
Yes, sir.
And if this is, let's say, I0, I0 is slightly above because it has two components. If this is I0, how will I plot I1?
Parallelogram method.
Yes, correct. parallelogram method. So this, the reactive component will be, the resultant component here will be what? I 1 dash. Where is my angle? How will I show my angle? Angle will be shown over here, like this one. This is phi 1. This is phi 2. And this is my circuit diagram. Phasor diagram for load inductive, lagging power factor. Agree? Understood this?
Yes, sir.
Yeah. Please complete it. Then we'll go to load is capacitive and then we complete one lecture. Might be we might take a break and then we'll continue again. Today only. This is easier diagrams, but in the exam that entire practical circuit will come. So that also we'll see now shortly. Can I go to the next one now? Capacitive load. Yeah. In when the load is capacitive, agree na? So I2 is leading the voltage by 90 degree. Yes or no? Where angle phi 2 is less than 90 degree because it's not a pure capacitor. If it is a pure capacitor, we can draw it equal to 90 degree. So I2 leads the voltage by 90 degree, where by angle less than 90 degree actually. I1 is same as I1 will be similar I2 I0 plus I2 dash. Then what can we say? E1 is equal to E2 that we have seen. E1 is equal to minus V1 and E2 is equal to V2. We have done that. So can we start now? We will draw the reference phasor. This is phi. Okay. Now if I draw my V1 over here, where will this come? V2. I mean E1 where it will come down below, right? Here, negative y-axis. So this is E1. Now where will I draw E2? It's equal to V2, E2, which is equal to V2 dash. Okay? Agree? Yes or no? Now tell me
Yes,
where will I2 come? Because I2 and V2 के बीच में phase angle should be less than 90 degree. Where I2 is leading.
in the fourth quadrant.
Here, na? Correct?
Yes, sir.
So this is I2 dash. So where will, this is I2. So where will I2 dash come? Here, right? Yes or no? This is I2 dash. Acha. Tell me where is I0? I0 we already draw it over here like this. So if I take the parallelogram now, okay, so where will this come? This is I1. This is I1. So what is my phase angle? This is my phase angle. This is phi 1. And where is my phi 2? Phi 2 is over here. So phi 2 is the phase angle between P2 and I2, and phi 1 is the phase angle between V1 and I1. Agree? Hello? Are you following
Yes,
this?
sir.
So I'll give you two options. Should we finish off the remaining phasor diagrams, this one, and then take a break, or we take a break then finish the phasor diagrams in the next lecture?
Take a break.
Okay, as you all wish. So these three phasor diagrams where the load is capacitive. Have you drawn this completed? So these three phasor diagrams where the load is resistive, inductive and capacitive, here we have not considered R1, X1, R2, X2. So next time in the next lecture in half an hour's time, so right now it is around 3 o'clock, 3, 6. So 3:36 we'll restart again with the same meeting link, okay? Half an hour from now. So then we'll draw the phasor diagram of a practical transformer with R1, X1, R2, X2, everything together. Okay, now everything is together of a practical transformer with resistive load, with inductive load and capacitive load. So let's take a break now. Okay, so we'll meet after half an hour. All right.